what is the idea behind this modular function spaces? Where did it start? Okay, let's start from the beginning. Okay, so it goes like this. First of all, we go by classical normal vector spaces. So today is just a little introduction, and the next lecture I will get you to some little details, and then we move on to some open questions. So I will ask Kozlowski to join us to discuss some open questions to see how we can have some open problems to work on. Okay? So the classical normal vector spaces, what are these? And we really call them classical normal vector spaces. So first, we have Hilberts. That is the first one. Okay? So Hilberts, we have nuclear 2. Why? Because every Hilbert space, we can find through Gram-Schmidt a sequence of vectors which are bio-orthogonal. And for example, any Hilbert space. So remember, a Hilbert space is a vector space, so it's a vector space with a dot product. Okay? So once you have the dot product, you have the norm, and we can go back and forth. For example, how do you go from the dot product to, so it's bilinear, it's a bilinear form, and how do we get the norm? So the norm, okay, is given by the formula x dot x. That's the norm. And the way you can also, what we call the polarization identity, you can also find, the dot product from the norm, which is, we have to go norm of x plus y squared minus norm of x minus y squared. So this takes care of the norm of x squared and norm of y squared, and you're going to stay with 4, and you have to divide by 4. Okay, and this will give you the dot product. So you can go from the dot product to the norm, or you can go from the norm to the dot product. And this is how you can check that you have a Hilbert space. This polarization, this identity here, okay, you take the norm and you define this dot product. If the dot product is not bilinear, it does not satisfy the properties of the dot product, then you don't have a Hilbert space. Great. So this is the classical Hilbert space. And then we can prove that if it is a separable Hilbert space, it is a separable Hilbert space, okay, then we can find a sequence En, okay, that is total in H, okay, and orthogonal and normalized. Okay, we can do this. So as I told you, Gram-Schmidt, for example. Then in this case, for every x in H, x becomes sigma x dot En, from 1 to infinity. And you have this partial identity and all this stuff, that the norm of x squared is just sigma of xen squared from n equal 1 to infinity. So you see, it behaves like L2. Okay? So this is the example that extends, of course, the old Euclidean spaces. Okay? So really, from the Euclidean spaces, you get little L2, you get any Hilbert space. Okay? That's how it went little by little, and people start to extend it. And then people said, okay, what about other spaces, what they call Banach spaces or B spaces? I was looking at the book. I have a beautiful old book by Stefan Banach. I have it. I found this in my office, written in 1932. It's called Théorie des opérateurs. It's in French because Polish people, Polish mathematicians during the time of Banach, they were writing in French. So anyways, it's a very, very beautiful book. He calls them B spaces, like this, exactly like this. Okay, B spaces. Of course, why we know, because himself is not going to name them Banach spaces. because the book was written by Stefan Banach by himself, so he didn't call them Banach spaces, he called them B spaces. So these are just normal vector spaces with a norm that is complete. And the examples, okay, so these are of course the Banach spaces. And the examples are, other than the Euclidean and the Hilbert, are the classical ones are little LP. So this of course extends the little L2. Okay, for P bigger than or equal than 1. Then we have C0, then we have C, convergent sequences, and then we have little E infinity, okay, with the sup norm. Okay, so these are the classical ones. And of course these are discrete ones, sequences. But then people came up with, I mean, even during his time, I'm talking about during the time of Stefan Banach, with the capital LP and capital L infinity. Okay? So these are what? These are, in the case, of course, of either you take R with the Lebesgue measure. Okay? So these are, so you are defined on R, the entire R, on with the Lebesgue measure. So here it becomes like non-discrete. Okay? So this is the example of the sequence Banach spaces, and this is the example of here non-discrete Banach spaces. Okay, so here the problem when you work with LP, okay, over, let's say, even extend it to any measure on a measurable set omega. Okay, on any measurable set omega. So in this case, a function that belongs to LP, okay, will not be like given like the case of a sequence, like one element. So we have to be very careful, because in LP, in this case, if F is equal to G, mu almost everywhere, okay, what does it mean? It means that, of course, this is when you do a little bit of measure theory, huh? Lebesgue measure, not Riemann measure, not Riemann integrals. I'm talking about Lebesgue measure. So what does it mean? It means that the set X such that f of x is different from g of x, this set here has measure 0. Mu of this set is 0. Okay? So the two functions are almost everywhere equal. In this case, these two functions are the same modulo, mod mu. For the measure mu, it doesn't differentiate between these two functions. So for example, if you look at on the real line, on R, if I look at the function f of x equal, okay, 0 if x is rational, and 1 if x is irrational, okay, so this function for Riemann integral, this function is bad, okay, for Riemann integral. But if you go to Lebesgue, for Lebesgue integral, for Lebesgue, it's very good. Why? Because my function f of x is just 1. Because the set of rational numbers has measure 0. And therefore my function is constant equal to 1. Okay? So this is just a slight difference that we have to be very careful when you are in LP of omega mu. Okay? Then we don't have f, like, we don't look at f as a function by itself. It becomes like a class of functions, okay? Meaning, so the class of f, here, G belongs to class of f, if and only if f is equal to G, mu, almost everywhere. You see? So it's not like an individual function, okay? It's like a function, it's a set or a family of functions, and they all have this property of being equal up to a set of measure 0. Okay? Great. So once you have done that, then for the integral, okay, the integral of a function like this, whatever you do to it, huh? So if you take, for example, absolute value of f of t d mu of t over omega, okay? So this will be the same as g of t d mu of t over omega. I'm assuming, of course, that the two integrals do exist. If they do exist, they're equal, because the two functions, they have. So you see here, this number, this integral, has nothing to do with what? With the individual functions, because all the functions are equal almost everywhere. So it's all part of that little measure theory that we studied before, okay, on Lebesgue measure. How do you go from Riemann integral to the Lebesgue integral? For the Riemann integrals, we don't have this problem. Every function is individually, it has an individual integral. But for the Lebesgue measure, no. Okay, so the Lebesgue measure, if two functions are almost everywhere equal, they have the same integral. Okay, great. So here, what is LP? So again, let's go back to LP over omega g mu. I'm sorry, g mu or mu, not d mu. Mu. So this is just a set of functions, okay, defined from omega into r, okay, such that what? It's measurable, of course, measurable. And the integral over omega of absolute value of t to the power p d mu of t is finite. Okay, this is the LP spaces. Okay, so this extends the little LP, because if you take n with omega, omega equal n, sorry, and mu is the counting measure, then little LP of omega mu becomes exactly little LP. Okay, the little LP. So people got interested. Of course, I'm taking p between 1 and infinity. Okay, the case of p equal infinity is also defined, but slightly different from the definition of capital P. And in this case, we can show that capital P of omega mu is a vector space. So first, because all the properties of measurable functions, and we can show all the properties of sum, multiplication by number, and everything is satisfied. So it's a vector space, number one. Number two, we can define that this object, okay, this object, which is the integral over omega of f of t to the power p d mu of t to the power 1 over p, okay, this defines a norm. This is amazing. This defines, okay, a norm on LP of omega. So we get now a normed vector space, and we can show that LP with mu with this norm, okay, is a Banach space. So this is an example of a natural extension from little LP to a capital LP, and they came up. This came up right away. I'm talking about 1932, right at the beginning, 1930. So these spaces are part of what's known as classical Banach spaces. Okay. So then, let's focus LP and capital LP. Okay. So I told you that little LP can be seen as a capital LP where omega is n and the measure is the counting measure, the discrete measure, or the pure atomic measure. Okay? Great. So in this case, what happened is that once we have done this, people started to look for extension. At the beginning, I'm talking about in the 30s. How do you extend these spaces? So people looked at the definition and they came up, okay, t to the power p, how does it look like when p is bigger or equal than 1, okay? So if p is equal to 1, you get t, okay, this is t, okay? And t to the power p when p is bigger than 1 looks like that, okay? So it's a convex function, okay? Why? Because if you take t to the power p and you take two derivatives, you will find p minus 1, t, p minus 2. So p is bigger than 1, so this is positive, therefore your function is convex. So t to the power p is convex. Okay, number 1. Number 2, t to the power p at 0 is 0. So it starts here. Okay, so it behaves like the case, in other words, this is like, so what they want, these are the basic properties, okay? There are other properties, of course, but for the time being, these are the basic properties. And people offered the following. They said, okay, let phi of t be a function that satisfies the same, b from r into r, okay? Let's start with r plus. Let's stay in r plus, okay? And zinc, like t to the power p, convex, and phi of 0, or t equals 0, and only if t equals 0. So there is only one point where this function is equal to 0, is at 0. And now they define little l phi and capital L phi. Okay? So what is capital L phi here? Okay, so L phi is going to be of omega over u. Okay, so it's f going from omega into r, such that measurable, okay, and the integral over omega of phi, absolute value of f of t, dv of t, is going to be finite. Okay, so now, so this is the guy who did this, by the way. Let me give you his name. Okay, Orlicz, okay, a Polish mathematician in the 30s, right there at the beginning. Okay, he came up with this extension, and he said, okay, so what's the norm now? Okay, so what's the norm? What is the norm in L phi? Okay, now things becomes interesting. What is the norm? It's not as we did before, the capital L P. Here is slightly different. So what he did is, okay, let us look at the set where the integral is less or equal than 1. So let's see. Okay, so this is f such that the integral of this dv of t is less than 1, this integral. So you can see, because C is convex, that this set C is convex, closed, non-empty. Everything is nice. C is very nice, balanced, and everything is nice. So here, C is convex, balanced, okay? It contains 0, okay, the vector 0, okay? Because phi of 0 is equal to 0, okay? And closed, C is also closed. If phi is nice, continuous. I'm sorry, because convex cell is closed. Okay. Okay. Nice. So what he did, he took the Minkowski function. Okay, Minkowski function. And that is the norm. So the norm of f is going to be the infimum of alpha, such that the integral over omega of phi of f of t over alpha, this is the mu of t, is less or equal than 1. Okay? So now this becomes a norm. So this now is the norm. And if you take the case of phi of t equals t to the power p, p bigger than 1, then you get that the norm of f is exactly the integral of f of t to the power p dv of t to the power 1 over p. Okay? So this, in fact, is what was offered by Orlicz to expand this LP. And then somebody said, okay, Modular, I think he's still alive, by the way. Okay, Modular came up with another one, okay, expanding on Orlicz's work. So instead of taking a function now, instead of taking a function of one variable, they took a function of two variables. So let's call it t and x and t, okay? Or omega and t, sorry. Omega and t. So then you consider the functions when you integrate over omega, absolute phi of omega, absolute value of f of t, d mu of t. Okay? So it becomes more general than the one we have there. And then, of course, they put more, like the soup of a family, etc., etc. So there are more and more complicated examples. But keep in mind, the classical Banach spaces are the LP spaces, and people start from there to see how we can build new spaces. Okay, new spaces. Excellent. So in the case of now modular spaces, what happened? So here what we have is, as you can see, so how did people start thinking about modular spaces? Which is, by the way, it goes back to the first one who did this issue of modular, okay, approach. It was Nakano, a Japanese mathematician. Okay, he's the first one. Okay, so what he did, he looked at now. You see, if you look at the norm, this norm here. This norm is not natural. And I know for the people who are working on this one as well as this one here. So if you look at this, this norm is not natural. It's defined in a very awkward way. The infimum of alpha is such that. And I know the people who worked on proving some theorems, like uniform complexity. When do we have uniform complexity, strict complexity, reflexivity, or the dual space, what's the dual space, etc., etc. That we are working on the geometry of Orlicz spaces and Modular Orlicz spaces. It's very, very complicated. It's a lot harder than capital LP spaces. So the norm is direct and easy to compute. So what Nakano said, he did the following. He said, okay, what was the norm again in LP? Okay, P bigger than 1. So he said, this is the integral f of t dv to the power 1 over p. So if I take everything to the power p, I will get this. Okay? So if we go now to Orlicz, okay, so we don't have isolation, okay? Isolation is gone. But we do have an object, which is what? This. Now what is this? Or what are the properties of this? Okay? So if we put this as rho of f, then the norm, as we said, is equal to the infimum of alpha positive, such that rho of f over alpha is less than 1. Right? It says, of course, I'm assuming, keep in mind, I'm assuming that phi is what? It's convex. Okay? That was part of the Orlicz example. I did not expand this on some weird cases. Okay? So here, Nakano paid attention to this object, this new object. And he said, what are the properties of this object? And he came up with the following, okay? So, number 1, rho of 0 is equal to 0. And rho of 0 is equal to 0. And rho of f equals 0 will imply that f is equal to 0 almost everywhere. Why? Because we said, remember, that phi of t equals 0 if and only if t is equal to 0, and phi is positive. So we have these properties. Okay, if we have 0, we have 0 for rho, and if it's equal to 0, then you have almost everywhere 0. So it's almost similar to the norm, right? The norm of f equals 0 if and only if f is equal to 0. Number 2, and this is very important. What is rho of alpha? Now we have a problem. Okay, so this is going to be the integral of omega phi of alpha f of t d mu t. And as you can see, there is no way alpha will come out, because it depends on phi, the function phi. Okay? So here we do not have rho of alpha f equal absolute value of alpha rho f. This is not true. Okay? But if the modulus of alpha is equal to 1, okay, but rho of alpha f is because we have I'm sorry, here I forgot to mention that it's going to be absolute value of alpha times f. So if this will be the same okay, if alpha is equal to 1, we get rho of alpha f is equal to 1 rho of f. So this is true. What's not true is that you cannot take alpha out. Okay? Great. More, if alpha, absolute value of alpha, is less than absolute value of beta, because phi is increasing, then we can show that rho of alpha f is less than rho of beta f. Okay? If alpha, absolute value, is less than absolute value of beta. Great. What else? This is 2. So we don't have 3. What happened to rho of f plus g? Okay, rho of f plus g. This is the integral of omega phi of absolute value of f of t plus g of t d mu of t. Okay, fine. So now this will be less than phi of absolute value of t plus absolute value of g of t. Okay? But d mu of t. Okay? But there is no way we're going to have this less than this. This will only happen, okay, phi of g of t, d mu of t. Okay? This will only happen if phi is subadditive. So if phi is subadditive, then we have one rho of f plus g less or equal than rho of f plus rho of g. This is true. But if phi is not subadditive, okay, and there are many examples, like for example, if we take phi of x equals e of x minus 1, okay, this function has all the properties. It is convex, increasing, and it's only equal to 0 at 0, and is not subadditive. Okay? So if it is not subadditive, then we have a problem. So we will not have rho of f plus g may not be equal, less or equal than rho of f plus rho of g. Okay? But we do have something. We do have convexity. Rho of f plus g over 2, this is true. Rho of f over 2 plus rho of g over 2, because phi is convex. Now I use the convexity, right? So in particular, we have rho of f plus g is equal to what? Look at now what we have. It's very interesting. is rho of 2f plus 2g over 2. This is less or equal to 1/2 rho of 2f plus rho of 2g. And since 1/2 is less than 1, this would be less than rho of 2f plus rho of 2g. I didn't say, be careful, because I could have said rho. I know that rho of f is less than rho of 2f, yeah, because that's what we said, 2 is bigger than 1, okay? But this will only give me, this property will only give me that rho of f plus g is less than rho of 2f plus 2g. That's not what I'm saying. I'm saying rho of f plus g is less than rho of 2f plus rho of 2g, not rho of 2f plus 2g, okay? Great. So now we don't have what? So we don't have the triangle inequality. Okay? That's not true. But we do have something not far plus rho of 2g. Excellent. Now be very careful, because next the question becomes if f belongs to LP, okay? In other words, no, I'm sorry, not LP, no, because that's a Banach space. I'm not talking about LP. I'm talking about, okay? If f is such that what? Such that this integral dt is finite, what happens if I take now 2 times inside p 2 times f of t? Is it or not? So sometimes the answer is yes, sometimes the answer is no. Okay? So it depends on phi. Okay? So when the answer is yes, the answer is yes, if and only if, is what we call the delta 2 condition. Okay? So the integral of 2f, according to phi, of course, with respect to phi, has a finite integral if and only if the integral of phi of 2 times f is also what? Finite. Okay, so this is what we call by the delta 2 condition. But there are examples, like the one I just gave you, which is ex minus 1. This does not satisfy the delta 2 condition. Yeah. And in this case, we may have this integral, which is finite, but this integral is not finite, it's infinite. So in this case, you do not have, this is out. Okay? Even this you don't have it. Okay? So now, Nakano, okay, Nakano, back to Nakano, he introduced a modular rho on a given vector space X. So you take a vector space and he defined the concept of a modular function. What is a modular function? So it's like a norm, but it's not fully a norm. And he got all these ideas from these LP spaces and all these spaces I told you about. So he came up with this concept of module, and it satisfies some properties. Okay? So once you have a modular defined on a vector space, the vector space now X with this is called a modular vector space. Okay? Modular vector space. Like what we did with normal vector spaces, we have now what's called modular vector spaces. Okay? This is Nakano around 1950 something. I forgot 50 something. I can get you I think it was 1959 if I am not wrong, but I'm not sure. Okay? So the beauty here is what can we say? What are the properties? And it's really interesting because remember we fail if you take two vectors x and y, we do not have this. And since we don't have this, okay, some commonly known properties, which is that xn converges to x in the sense of rho, if and only if rho of xn minus x goes to 0. Once you have this, okay, you cannot claim now that xn is rho Cauchy. Okay? So in other words, you cannot say that rho of xn minus xn is small. So we can say it in the case of what? If we had a triangular inequality, yeah, but not in terms of what? Of the module, because we don't have the triangular inequality. So in this case, Cauchy behavior and convergence are totally different. Totally different. Okay? So next time, I'll be talking about a little bit more about this modular business, and specifically to look at modular function spaces, and even in the absence of the triangle inequality, okay, what can be said? For example, how can we define conversions? How can we define completeness? How can we define, like for operators? And then, of course, we jump afterward and start working with operators, etc., etc.